Welcome everybody to today's video. Today I think is going to be a fun day because, or I guess kind of the wrap up the week, we'll start actually doing some assembly. So we'll get into doing a sample program. We'll go through some code today, and that you'll have, once I'm done going through this sample code, I'll upload it, I'll make it available in our Google Drive under the code folder, so you can take a look at that. I would highly encourage you to take that code and either follow along as we go through the video today, or take that code and upload it and execute it and just start doing some of these basics, get familiar with building the projects, getting them to execute. We're going to talk about probably, the biggest takeaway today is the mnemonics and how do you actually write this to get these instructions to execute. As well as we'll look at some kind of debug stuff that allows us. There's a function that was written by the author of the text that we use called dump regs, and the dump regs will allow us to dump information about the registers, which will help us, I think, here, especially initially, in understanding kind of what's going on in our program. So you'll see here when we get going, I've already created a project, and we use that script. You don't have to, but it's there hopefully to make things a little bit easier. Create a project. I actually called it not hello, but video 07, and so I'm going to name the code as well as any projects that I'm working on the same name of the video number so that the code will match up with our schedule, and again, hopefully make that a little bit easier to find. We'll use this for today, and we'll get right into it here. So what is a mnemonic? Well, a mnemonic is basically a one-to-one mapping between the opcode, the actual machine, the binary, and something that we as human beings can understand a little bit better. Again, for programs, for the computer itself, it really doesn't care. Ones and zeros are how it operates anyway. We need these languages, these mnemonics, and things at these higher levels in order to help us actually write them. Let's say, for example, that we want to add EBX to EAX, and then store the results in EAX. And so in hex, we would see that that instruction in this, right? That would be that instruction. You could write that in binary, in which case then each one of these hex digits is 4 bits. So we could write that all out, and no, 100, sorry, let me just erase that, maybe. Right, and that would be the same instruction. So that would be the binary to say add EBX to EAX and store the result in EAX. Right, this is very difficult. This would be very difficult for us to do as human beings because we'd have to remember these codes in order to write our program. So it becomes much more difficult. It also changes with processors and architectures. And so if we move between x86 and x64 and ARM and Spark and everything that's out there, then we have to learn a whole new set. And so this becomes very challenging, very difficult for us to do. So with mnemonics then, it makes it a higher level. It makes it a little bit more readable. And that this mnemonic add to EAX, EBX becomes a lot easier for us to read. It can also remain consistent against the different architectures, against the different machines. And that when we'll use an assembler, when we assemble this into, and the assembler assembles this into machine code, it'll turn it into the actual ones and zeros for that particular architecture, just like with a C program. We can build a C program for a variety of different architectures, 32-bit, 64-bit, whatever. The compiler does that work of actually generating that machine code for us. The first portion then is called the mnemonic, and the rest of it is followed by the operands. So this is our mnemonic, this is the instruction that we want to execute, and what comes after that is the operands. It's like the arguments to that instruction. We can have 0 to 2 operands. There is a difference between an assembler and a compiler, and we won't go too deep into the difference, real hardcore the difference between the two. That is something that we do talk about more in the reverse engineering course. With an assembler, you get approximately on a one-to-one assembly to machine code. So that is that when you type a command, add EAX EBX, then you get one instruction for it in actual machine code. With a compiler, you can have one line of code, and that can generate many lines of assembly or machine instructions, because the compiler will, you may have in one line of code something like this. Let's say even something like this. You may have actually several operations, several instructions that need to take place in order to in assembly, in order to get this this equivalent statement to run. And so this is more of a one-to-one with compilers. It's not typically a one-to-one. This compiler makes things a little bit more portable because we can extract some of the details that handle the differences between the platforms as the compiler generates ultimately that machine code for us. Machine dependent, can be machine dependent, and for the course we'll use both. We won't take a look at the actual template files that we're using right now at this point. If you're interested, definitely take a look at those. Not only the template files, that project that we extracted early on in the semester, but also when you create a project, what are the files that are included inside of those directories? Your shell script, that .sh that we use to build that executable. Take a look at that as you get interested. We'll probably look at it here towards the end of the semester just to kind of wrap up here and make sure you understand exactly what's happening throughout that process. We'll be using NASM. So we talked about in the introduction to the course several different assemblers that we could use. NASM is the NetWide assembler, NASM for short. One of the main reasons we choose this is because, again, we'll use it for the RE course. It's very common to see NASM or the use of NASM as well. But then additionally, we'll be using GCC and C to create our programs. Although, for the most part, you'll be able to just run the script that's been uploaded or that's generated in your projects throughout most of the semester in order to take your code, compile it, link it, and actually get something that's executable there. So what is an operand? Well, those operands are like arguments to that instruction, that mnemonic that we're calling. Typically what these operands are going to do is they're going to modify a register or a memory location. And so like you saw with the single example that we looked at already, if we have an add EAX, EBX, then we have the instruction, the mnemonic is add, and then these two are registers. We might have add EAX 7, right, where this operand then becomes a hard-coded value, an immediate, which was actually this right here. And so we can use registers, we can use memory locations, we can have hard-coded values in which you'll see that value directly in the code. It might be implied, and implied being an increment, and the implied is to add 1 to that current register. So let's look at some examples, very similar to the one that we just looked at in the previous slide. Here's our mnemonic. So we're going to say move into EBX, a hard-coded value of 7. And what can trick people up, especially getting started with assembly here, in this particular syntax, is that this is the destination right here, and this is our source. So we're saying move the rightmost operand into the left, right? Move 7 into EBX. EBX and 7 in this case then are the operands. They're both operands, but in our operations, usually this first value is the source or the destination. The second operand here is going to be the source, right? So you just got to keep that in mind, and that's the direction that things are moving. We're moving in this direction here, and most commands are going to be like that if they have two operands. Same with this. Move into EAX, EBX. And so what this command is doing is it's simply saying move whatever is in EBX into EAX. Move the contents of EBX into EAX. Right, now these instructions, as we talked a little bit about in one of our previous videos, depending on the size, depending on the operand, depending on the register that we use, that's the amount of data that's going to be transferred. In this case, because we're using EAX and EBX, we're transferring all 32 bits of EBX into all 32 bits of EAX, right? And keep in mind then, especially with these general purpose registers, that we can reference different components of it. We can reference EAX, we can have AX, AL, AH. For EBX, we could reference BX, BL, or BH as well. And the same with EDX and ECX, right? So we can move different amount of data into different registers. And we'll talk more about that here down the road. Here's an implied, so increment EAX. So what's that going to do? Well, that's going to take whatever value, 32 bits in EAX, and it's going to add 1 to it and then store that result into EAX as well. All right, so it's not just incrementing EAX, but it's incrementing it and storing it in EAX as well. And the same is hold true for decrement, except we're just simply moving in the other direction. We're subtracting a value. So here's the common format for your mnemonic. You'll see with these, the portions here that are in brackets, square brackets, those are optional. So you may have a label, and we will use label. We'll talk about labels here in, relatively soon. Label is just there to help us identify a certain location within the program. So you may have a label. A label will be some value followed by a colon. We'll have the mnemonic. So what is the instruction? And then we'll have any number of operands, 0, 1, 2. And those operands, much like we've talked about, then become immediates, registers, and memory locations. Additionally, you can have at any line, in any of your lines of your program, you can have a comment. And a comment in assembly is going to be the semicolon there. Comments, much like in C, 2 forward slashes, and that it's a single line. So make sure that there is no block level. That is, you can't just use a certain character to comment out a block of code. This will just give you a single line. So make sure that you're just aware of that. If you're not expecting it to use the semicolon to get multiple lines of code commented out. It's only going to do that line, so you can see. And I would encourage you to do this, especially as you're getting started. When you write out your instruction, put a semicolon, put a comment behind it just to tell yourself what it's doing. Build that out, kind of talk, almost like you're talking to yourself as you're building that program. So we have a variety of mnemonics, and we'll go through most of these here now as we move forward and we go to more advanced examples. Moves data. We'll look at a couple of examples here with move. We'll look at some examples with add and subtract. So we're going to add 2 registers together or add a value to a register. We'll talk about multiply a little bit later on, as well as jump and call, again, as we get further along in the course. Right, directives. Directives are not actual instructions. They tell the assembler to do something, such as setting the size of the stack, defining memory, defining constants. So we'll do some of that here, not necessarily today, but more likely into week 3. We'll start, as our programs get a little bit more complex or a little bit more advanced, start using those defines. We have %define, those directives. %define. It's like hashtag define in C. If you use that or have used that before, you may see this in assembly. And what it's doing is it's essentially defining like a shortcut. That is, that we can say that we've defined this keyword size to have a value of 10, and then anywhere in our code we can use size instead of 10. And when the program is actually run, once it's assembled and executed, once it's assembled anyway, wherever the assembler finds the word size, it'll replace that with the value 10. And why something like this becomes important is because maybe you're going to use that value all over your code. You're going to use it in several locations, and that may change. And so if that changes, let's say that you have, you define some hard-coded value of 10, and you're using it to control your program, and you use that in 15 locations. If for some reason you have to change that, now it's a 12 or a 15, you can just change it right here, and it'll trickle throughout your code when it's assembled. The alternative is to go through and you manually change that yourself, which tends to be error prone. You tend to miss a spot to make that update, which makes your code not work the same or the way you expect it, and adds debugging. And so defines can be pretty helpful. Use those if you like. Okay, we'll use these data directives frequently, and that what these do is they tell the assembler to reserve a certain amount of location, a certain amount of memory for us. So the first, so you see DB, DW, DD, DQ. This first D stands for define, and then the second portion of it stands for the quantity, the number of bytes essentially that we're looking for. So DB is defined byte, so a byte, 8 bits. And that's the smallest amount of space that you can allocate. That's that ASCII char that we talked about earlier. Define word is 2 bytes or 16 bits. So 2 chars, Unicode, we just have more space available. Define D word, double word, right? We talked about that as well. 4 bytes or 32 bits. And so this is basically going to be as much as we're going to allocate that since we're using just 32-bit for the course. DQ, quad word, is 64 bits. You can see that more with a 64-bit environment. Pointers are 32-bit. So when you define a pointer inside of, like your C program, a pointer, then the value of a pointer is a memory address. and that memory address is 32 bits, right? Because that's what we have available for those addresses. If you think back to the virtual memory that we talked about earlier, those addresses can go from 0 to which is our 32 bits. So that's how we define. Now, understand, what this is for. This is allocating memory. We're saying define a byte. Give us 8 bytes in memory. Give us 16 bits in memory. Okay, so sorry if I misspoke there. Give us a byte. Give us 2 bytes. Give us 4 bytes. Allocate that space in memory because we're going to use it to store things in it. It's going to become an integer. It's going to become a pointer. It's going to become an array. We're going to move data into that. And so we're requesting that space so that we have it there for our use, for our storage in our program. Identifiers, we'll use identifiers as kind of like defining variables. We can also define constants, procedures, labels, and we'll do all of those here as we get more into the code. Here are the restrictions. And so take a look at this. Just like any language that you're going to use, how you define your variables, the syntax, the valid characters for defining variables are going to be defined somewhere in that language. So you can see here the valid characters and labels, letters, numbers, these special characters. The only character which may be used as the first character of an identifier are letters. And so again, you typically have rules like that because other characters at the beginning of something else, something that's syntactically significant to that language, might mean something different. So, read through that, and you'll just, I guess, the takeaway is just like when you're learning any other language, if you're running into syntax errors, when you go to build your program and you're getting syntax errors, just make sure you're not doing something wrong. You're not using an identifier that's violating these rules, and that's actually what's causing your syntax error. All right, so at this point, we're going to go ahead and just go through some simple examples here to get used to working with assembly. So we'll have a sample program. We'll do some of this. We'll do a lot more than just this, but we'll do some addition and subtraction. We're going to use the dump regs example or that function because that's going to help us to see what's happening in these registers. So with that, let's see. I'm going to bring up my environment. So what I have open right now is I have a terminal, which is going to be open to the project that I created. So I created a project, gen.sh, and for this one I called it video07. What I also have open then is some code here. And so this is the ASM file that was inside of that project folder. So I've already built this project. So you're going to see that there is the additional, the .o, the object file, out, the executable. But when you build these projects initially, you should have the include, the .asm, and the .sh. And then in order to get that to run, just as a refresher, then you can say ./video7.sh, and that should generate everything for you. If you have syntax errors, if there's a problem, you'll see some output here. If not, then you'll have video07.out. What I'll probably also do, because I typically want to build and then run at the same time, you can use the double ampersand, and you can say if the first command executes successfully, then go ahead and do this next thing. So I can say build it and then run it at the same time, and you can see there's nothing in the file right now. The next thing here, the other thing that I want to point out is that I have this open via a text editor. And so if you want to download something like FileZilla or CyberDuck and you want to connect like we have, like I've explained in a previous video, you want to connect to that and you just want to edit that file through there so that you can edit it in a text editor natively, that's fine. That's fine with me. You'll make changes here. You'll save the file. It'll have to get uploaded before you can actually do anything on the, build it and run it again. Otherwise, your other option is just simply to use a text editor, Nano or Vi, and edit that file, your ASM file here, directly from your command line, your terminal. So either one is fine with me as long as you can get it to work. That's really all that's important at this point. Okay, so we're going to start off with, and we're just going to focus on a very simple example. And so we're going to you can see that there's some comments that have been added. Start here and end here. And we'll talk about what all this stuff means a little bit later on in the course. But for right now, just want to start in between these two lines of code. So important, it happens every semester. Somebody's not paying attention and they start adding instructions down here, down here, down here. Your program's not going to work. It's probably going to, if it doesn't generate a syntax error, it's probably going to not run when you go to execute it. So we want to make sure that you're in between these two comments. The first thing that we'll do is we'll say dump regs with an argument. And what this is going to do is it's going to dump the registers. So we'll go back to our terminal here and we'll run that example. And you can see, I'll make this a little bit bigger. There we go, that's a little bit easier to read. There we go. All right, so I'm going to clear the screen. We'll run that one more time. And you can see that this is the information for the register dump. I said dump reg 0. What that 0 simply does is it gives us the number, that value right there. And the reason that is because you can, as your programs get more complex, they get longer, you might have this dump regs in multiple places. And this is just your way of keeping track of it. Dump reg 0, dump regs 1, dump regs 2. It has no impact on the output other than this little title here. It's just a way to keep track of that. As far as the output then, here you can see, here's our registers. What's the value inside of this register right now? It's FF9F0E2F. What is that? Who knows? We don't know, because that was just the state of the register at the time that our program ran. And so oftentimes when registers are done being used, they're not cleared out, they're not zeroed out. And so this could be data, this could be a pointer, this could be a memory address, this could be all sorts of things. But it doesn't really matter. We just need to keep that in mind, that before you use a register, just keep in mind that it may have data already in it. So you may need to clear it out. You may need to zero it out. So there's all the registers, EBP, ESP, EDI, ESI, EIP. We'll talk more about some of these again as we get further in the course. We have the flags as well. So right now, for whatever reasons, the sign flag is set and the parity flag is set. You may see CF, you may see ZF, CF being carry flag, ZF being the zero flag. So that's what we're looking for, right? So what if we do this? Inside of our code here, we say move into EAX 0. We save it. This is what EAX is right now. Now we go ahead and run that, and we can see that EAX is now 0, 0. All bits have been set to 0, right? These are not bits. These are hex digits, right? So each one of these represents 4 bits. 4, 8. So this would be, I'm having a hard time getting this to select here. That would be AX. This would be EAX. This would be AL. These lower two would be AL, and this would be AH, right here, right? Because for each hex digit, we have 4 bits, right? 0 through 1111. That's 0 through F in hex. And so each one of these represents 4 bits. So we have 8 times 4, which is our 32. Right, so move into EAX 0, and that zeroes that out. And you can see EBX has a value in it, and in this case, it's different than the last time that we ran, because we don't know what's in there. You can XOR. So if I say XOR EAX with EAX, and save that and run it, you'll see that we get the same result. EAX is now all zeros. Okay, so something else that you'll notice. So let's save this again without any moves, and we'll see that EAX has another value in it. Let's say that we move into EAX a value of 500 hex. Okay, so that is the number, and this H represents that this is a hex value, so it's 500 in hex. You may also do it in that format there. And if you want, a semicolon, move 500 hex into EAX. You can leave a comment. Now, this is pretty self-explanatory, I think, that you're moving 500 hex into EAX. Where these comments will probably become more important as you start to build out a program, and you're helping to kind of map the logic of the program through the code. So regardless, don't be afraid to leave comments. Okay, so what'll happen then? Right, we only moved 500. 500 isn't necessarily enough to consume all 32 bits, but because we moved it into EAX, that set the entire register to the value 500. So all these leading bits got set to 0, and we have the 500 set. Okay, all right, so let's go ahead and let's do something else. Let's move into, or let's add to EAX 200 hex. And let's see that run. I'm going to clear my screen. Right, and there we go. Right, so we added to the current value in EAX, which is 500, value of 200 hex, and then we stored the result in EAX, which we've done there. Okay, we can also use additional registers. So let's say that we move into EBX 100, and now we add to EAX EBX. And you can see that our result is now 800. EBX has a value of 100, and EAX has a value of 800. Right? EBX is going to maintain that value now until our program's done, or until we change the value in that register again. Right? So we set it there. We're not going to necessarily, in this program, we're not going to use it again. So it's going to maintain that value until something else uses it. So that's why when we run the program, we get garbage inside of these registers, because we can leave that garbage behind and something else will get it when it gets access to those registers. Okay, we can also subtract. So we can say subtract from EAX EBX. And the result will be negated essentially, and that will have a value of 700 now. All right, let's see, what else do we want to look at? Let's look at a couple other moves. So I'm going to leave these in the code here, and we'll move down to kind of a new section. Let's say that I want to move into EAX. Right, and then let's dump regs 1. So we'll see 2 register dumps now after this program executes. Right, so there's 0 and there's 1. Okay, what did I do? I moved into EAX 8 hex digits of F, so that means that essentially sets all bits, all 32 bits in that register to true or to 1. You can see EAX now has a value of FFFF. Let's say that I move into AX a value of 0. Right, you can do it with that syntax, you can do it like that, doesn't matter. Now what happens when I run this code? Okay, you can see here that we moved into AX 0. So that lower 16 bits got set to 0. Those upper 16 bits were left F because we didn't touch them. We set them to 1 in this instruction. We didn't touch them in this one. Right? And as you might imagine, if we say move into AL 2 and move into AH 3, there's our values, right? So those upper 16 bits are still the same. The upper 8 bits of AX get set to 3, and the lower gets set to 2, because that's what we reference. That's the register. So when we're dealing with portions of a register, we're only changing the bits on that particular portion. 32 bits, 16 bits, 8 bits, and 8 bits. And so here, it doesn't hurt to just say, maybe leave a comment to say all 32 bits. And here we'd say the lower 16 bits. And this would be the lower 8 bits of AX. And this is now the upper 8 bits of AX. All right. All right, now we can keep doing that. So again, at this point, just go through some of these examples, right? Move some code around, move some values, immediates from other registers, addition, subtraction. We'll talk about multiplication and division here soon. Dump regs, make sure that you can call that, and make sure, most importantly, that you can look at this output and understand what's going on. That you can write a few instructions. You can say, okay, I know after I do these three instructions, I know the state of my registers. I know that EAX is going to have this value and EBX is going to have this value, and then dump the registers and see if you're right. Right? That's the biggest thing that you need to be able to understand right now. All right, so I'll get that code uploaded. A couple more things here, just in the slide deck. we'll talk about something called a listing, and we won't probably do a ton with this here this semester. This is something that, again, is another one of those things that if you're looking ahead and you think reversing or 444 is in your future, or if you're just interested more in this, we'll get more into the listing type and the information that comes from this down the road. It's useful for finding errors when you want to generate a listing. What you can do is, you can, using NASM, this -L option, and get my pen back. There we go. -L, and then the name of the listing file. And then once you do that, this would be an example of results. So you can see that this is in a sample program that I created. Here's a label, ASM main, which you do see in our template code. It's not all that important right now to understand all of what this program is doing. You'll understand it here in a few weeks if you don't already, which I'm not expecting anybody to. What's interesting about it, though, is that you're seeing, as we talked about that machine code, you're seeing that those instructions and how they map to the mnemonics. So 39C0 is compare EAX, EAX. B8, B8 is the instruction for move EAX, and in here we moved 100 into EAX. So this is then 100. This is the operand, right? So that's kind of where it's interesting. Subtract from EAX1, right? So 2D, that's the actual opcode for subtract EAX, and this is the value, 1. Now, one thing that you may be noticing here is, well, if this is 1, this does not look like 1 to me. This looks more like 1 million. Well, there's something called endianness, and we'll talk about endianness later on. It's the way in which the bits are ordered from most significant to least significant, and most of the times computers store in little endian. That means that the least significant byte comes first, and the most significant byte comes last. And so you'll see here that this is, while it looks like it's backwards to you and me, it's just the way that the bytes are stored. All right, the other thing that you'll want to notice is when functions are called. And so you can see here that we have this instruction right here, call print string, and you can see that E8 is call, but then we have these parentheses with all zeros. Well, what does that mean? Well, that is because we're looking at something that hasn't been linked yet. There's a process that when you're building an executable, static linking or dynamic linking, that we need to know the address of that function. And we talked about memory addresses, and we need to be able to know where to jump to in the address space in order to execute that function. And so when we generate this listing, we haven't done the actual linking. So this is really just a stub saying, yeah, you know, eventually when this program runs, an address will be automatically filled in here so we know where to go. And so that's what you're looking at when you see that E8 and then this empty value. Statically linked, you would see an address. Dynamically linked, you don't. Statically linked means that we have that library, like print string, we have it included in the executable. We know it's going to be loaded when the program runs into our address space. We know where to go. So you can look at this and you can see that this is in fact dynamically linked because there's no address there. Dynamically linked means that it's only going to load it once it's being run. And so it'll have this lookup table essentially, and that it'll go to that lookup table and then resolve the address at runtime. So you know, we'll get more into, well, I'm not sure if we'll get more into the static or the dynamic here, definitely in the reversing course. Right, you can also view data in executable. So XXD allows us to print out the actual data in a file. Probably not something that you'll find yourself doing too often, but I just did want you to know that it is available. So if we do XXD and then the name of our executable, so in this case video 07.out, right? This is the actual dump of, let's see if I can make that just a little bit bigger if that's easier to see. There we go. So this is actually a dump of that binary. So this is the actual binary. Sometimes you see things that look like ASCII, it's just because that's, you know, the way the characters are being represented. You could find the actual code here, the actual instructions. Here's the hex, and so just something that's maybe slightly interesting at this point. So with that, that is all I have for today. Again, I'll get the code uploaded, spend some time with that, whether you type it yourself or you upload that file and work with it. Really big thing is the mnemonics, getting the right format, getting your programs to build, moving things around and doing some basic things like adding, subtracting, and then being able to know what's going to be inside of those registers after that's done. Dumping those registers and seeing those values. So if you have any questions, if there was any issues in seeing my code, I tried to make the fonts what I think will be plenty big enough between the terminal here and the text editor. Definitely let me know that as well, and I can make adjustments as well as reshoot the video or something if I need to. Look at the code while you're following along the video. That will probably help as well. So I think that's it. I'll see you guys here. This will wrap up this week, and next week then we'll pick up and we'll do some more assembly.